Hello, Chem 151 students, and welcome to our second and final lecture for this week. It's about Le Chatelier's principle. Before we start, I just want to give you another reminder that the big thing this week is going to be practice, practice, practice. So you'll notice there's a few more homework problems than usual, and that may, be not quite enough to get you there. So just make sure that, you're coming to office hours if you need help, and even trying the sample problems and example problems in the text that give you the full solutions. And as I mentioned in the last lecture, that's really important. That this is all about practice here this week. So I'm not going to bog you down with too much lecture. I just show you some examples and then have you practice, and make sure to come to office hours or send me an email if you get stuck on the problems. For this second lecture, it's going to be about Le Chatelier's principle. So there's not really going to be much in the way of calculations here. I will use a few calculations to demonstrate the concept, but you don't need to use calculations to apply Le Chatelier's principle. So let's go ahead and talk a little bit more about it. And the statement of the principle is this: if a stress is applied to a reaction at equilibrium, a net reaction occurs in the direction that relieves that stress. And so what that means is that if a reaction is at equilibrium and you change something, the reaction is going to move in the direction that fixes your change. That change can come in a few different types. You could change the concentration of the reactants of the product. So if you add more reactants in, let's say, the reaction is going to move in a direction that's going to get rid of those extra reactants you added. Or if you take something out, the reaction is going to move in the direction that replaces what you took out. So the stress that they're referring to is a change that you made while the reaction was at equilibrium, and the reaction will have to proceed in such a way that it will correct that and go back to equilibrium. Another change that can affect this for gaseous reactions is the pressure of the gases. And so generally the pressure will be changed by changing the volume of the container it's in. So you guys are familiar with that. If you've got a balloon full of gas and you squeeze it down, what will happen is you'll feel the pressure increasing, right? And that is effectively an increase in the concentration of the gas molecules. And so that will have an impact on the equilibrium as well. Finally, if you change the temperature, that will also affect the equilibrium. So the equilibrium constant does depend on temperature, and so changing the temperature will have an effect on the equilibrium. Okay, and so that's something to keep in mind as well. So this concept of Le Chatelier's principle is extremely important in industrial chemical reactions, and also all kinds of chemical reactions like those that make pharmaceuticals. Here's an example of an actual reactor that is involved in the creation of ammonia. So we talked about this important reaction in the last lecture. It goes like this: N2 plus 3 H2 molecules makes 2 NH3. And this is in the gas phase here generally, but what you'll see is that there's little tricks that are done in an industrial reaction to essentially remove things from the reaction, or change the temperature in such a way to make the reaction happen more quickly and more to completion. Because what we want in an industrial reaction is to quickly get as much of the product as we can. And so in this reactor here to make the ammonia, which is used for all kinds of things, cleaners, fertilizers in particular. It can be used as a fertilizer directly, sprayed into the ground, or it can be reacted into something else like that makes a solid fertilizer that contains nitrogen. And so the nitrogen and hydrogen gases are fed into this column here. They are heated because the reaction will go more quickly if they're heated. That will, as we will see, drive the reaction forward as well. And then a catalyst is used to speed up the reaction here. And then all of these are mixed up, and so you have the hot gases mixed up passing through this catalyst, and along the way here ammonia, NH3, begins to be made. And a great thing about this formation of ammonia is that the ammonia, it has a lower boiling point than nitrogen and hydrogen. So once it cools off to closer to room temperature, the ammonia changes to liquid when it's not a little bit cooler than room temperature. And so finally, once the mixture here of nitrogen, hydrogen, and ammonia get over here, the ammonia can actually be removed from the reaction. And the result is going to be that when you remove the nitrogen from the reaction is going to push the reaction forward. The equilibrium is going to now move forward to replace that ammonia that's being released. Or that's being taken out of the reaction. And so this little trick is the way in which lots of industrial reactions can be made to make more and more products, and then ultimately, also because of the separation, we can recycle the nitrogen, hydrogen, and then feed it back into the beginning. And we can keep continuing to push this reaction forward and make more and more products because of the fact that we're removing the ammonia. And this is a trick that's done in many, many reactions. So just in general now, to state what happens when you disturb the equilibrium by adding or removing reactants or products, the concentration stress of an added reactant or product is relieved by a net reaction in the direction that consumes that added substance. So if you add something either on the reactant side or the product side, the reaction is going to move in the direction that uses up what you added. And alternatively, if you remove something, the reaction is going to move in the direction that will replace what you removed. So going back to our example ammonia here, it's the ammonia that's being removed. And so the reaction now will have to go forward to replace that ammonia that was removed and return to equilibrium. And so that's why this technique is so effective. Here is another example. This is actually an example from an experiment that you are actually going to do. You're not going to do it exactly with all these reactants, but many of them you're going to do. And so if we have a solution at equilibrium here, it is it's iron ion and thiocyanate ion in equilibrium with this iron thiocyanate polyatomic ion complex. This is what's known as a transition metal complex, and we'll be talking about those in the next chapter. But so there's an equilibrium between these, and the iron ion itself is yellow, and so this is like yellow, and most importantly, this is like a red color. Okay, this is like a red color. And so when the solution is becoming darker red, that means that you can, when it looks red, that means the reaction is going forward and producing more of the iron thiocyanate complex here. So if we add in iron chloride, so iron 3 chloride, well, this contains chloride ions, yes, but more importantly, it contains iron ions. So if we're adding iron 3 chloride into this beaker, what we're doing is we're adding more reactant. So we've added in here more reactant, and so I like to show it with a little arrow like this. So we're putting in more of the reactant and increasing its concentration. So now to correct that, to correct this stress, the reaction has to move forward or to the right, as we say. So equilibrium shifts to the right is another way of saying this, to remove the additional iron thiocyanate that you've added. And the result is that you see the solution become more red. Okay. Now, alternatively, we could also add more of the thiocyanate ion. Okay, so if we here are adding KSCN, that has potassium ions, but that's a spectator. It's not going to do anything. What's important is that this is adding thiocyanate ions. And so here again, we're adding more of the reactant. So we put in more reactant, and then the reaction must move forward to remove that additional reactant that we added. And so you see again, you see the solution becomes more red because the equilibrium has shifted to the right and more of the iron thiocyanate complex has been made. Okay. Now, The other thing that can happen is we can add something that will remove, let's say, a product. Okay, and so it turns out, and you're not expected to know this, but as it says in part D here, if we add oxalic acid, what we're essentially doing is we're adding oxalate ions, and those oxalate ions, those are going to react with the iron and remove the iron ions. So by adding the oxalate here, what we've done effectively is we've removed the iron ions from solution. They have now become this guy right here instead. And so the result is that now the equilibrium shifts left to try to replace, we're trying to replace the iron that we lost. So the equilibrium shifts left, and that consumes some of this iron thiocyanate, and so the beaker becomes less red because we have less of that iron thiocyanate complex. Okay. Now, one more example here is if we add mercury ion. So again, you're not expected to know exactly how this mercury ion is going to what it's going to do, but we're adding here mercury 2 chloride, which is going to dissolve. It'll make mercury 2 plus ions and 2 chloride ions. But what's important here is the mercury ion. So the mercury ion will attach itself to the thiocyanate ion. You're not expected to know that that happens, but that ends up being what happens. And that removes the thiocyanate ion from the solution. It instead becomes this iron thiocyanate complex. And so the result is that the reaction must shift to the left in order to replace the thiocyanate that was removed. And so as a result, the solution is much less red. The iron thiocyanate is consumed. So here you can see that if we added the reactants, either of the reactants, so in parts in these two, right here, we added reactants. So the equilibrium shifts to the right. Okay. And in this situation here, with these, we removed reactants. And so the equilibrium shifts left to replace the reactants that we removed. And so that's what Le Chatelier's principle is all about. If you make some kind of change, the reaction will shift in the direction that fixes the change that you made. If you add more reactants, let's say, the reaction has to go forward to consume some of them. If you remove some reactants, the reaction has to go in reverse to replace what you removed. Here's another example back to that industrial process. This, by the way, is called the Haber process. It has its own name. It's so important. You'll notice we didn't talk about the value of the equilibrium constant. The equilibrium constant is slightly less than 1. And so that's not ideal for a reaction process that we want to do. If we want to make a lot of product, well, we would prefer to have a reaction where the equilibrium constant is large. So that means at equilibrium there will be a lot of products. So the trick that we saw that was done in order to push this reaction more forward to make more ammonia is that along the way the ammonia is being removed, and so that will cause the reaction to continue to go forward. If we think of this in terms of Q, that's another way we can think of it. So if we calculate Q and compare it to K, that's a way to know in which direction the reaction is going to go. So let's say we have an equilibrium mixture of 0.5 molar nitrogen, 3 molar H2, and 1.98 molar NH3. And we disturb this by increasing the nitrogen concentration. So that's another way, is we force in a bunch of reactants to try to force this reaction forward. Well, let's calculate Q here and compare that to K and see, because that's how we determine, that's numerically, which direction the reaction will go, right? we already know just qualitatively from, let's analyze this qualitatively first. So what we've done here is we've added more nitrogen. So presumably, according to Le Chatelier's principle, the reaction shift right to consume the added reactants that we put in. Of course, we can calculate Q to verify this numerically. So if we're calculating Q, this is going to be the product concentration, NH3 squared, divide by our reactant concentration, nitrogen to the first power, also divide by our hydrogen concentration to the third power. So now we plug in our new concentrations. So the concentration of ammonia didn't change. It's still 1.98 molar, and we square that. But the concentration of nitrogen did change. At equilibrium, it was 0.5 molar, but now it's 1.5 molar. So we put that in there. And then the hydrogen is still 3 molar. And so we calculate our Q. Let's get our calculator here. Calculate our Q. 1.98 squared, divide by 1.5, divide by 3 to the third power equals. And so we get 9.7 times 10 to the minus 2, or 0.0968. Yeah, same number here. And that is less than K. So when Q is less than K, here, excuse me, when Q is less than K, so here's K, so Q is less than K, that means we don't have as many products as we need to get to equilibrium, or we have too many reactants. Well, that makes sense because we were at equilibrium, but we added more reactants, and so that drove the reaction forward. So the other way to see that it goes to the right, so this is going to go to the right because Q is less than K. If Q is greater than K, it goes left. Right? So this is just numerically verifying that, of course, you know, Le Chatelier's principle works out. We've been calculating Q and comparing to K already to know which direction the reaction is going to go. But this is just allowing, Le Chatelier's principle allows us a way to determine that without doing any calculations. We add more of a reactant, the reaction must go right to consume the extra reactant that we added. And so more reactants will be consumed, the reaction will go from left to right. Okay, so that's how we deal with changing the concentrations. That's what happens when you change the concentrations of things. Here's a graph showing that what was in the last example there. So these were at equilibrium, the concentrations weren't changing, but then we spiked in a bunch of nitrogen. And so the result was that the additional nitrogen was consumed, some of the hydrogen was consumed, some additional ammonia was produced, and then we returned to equilibrium again. So there's a new equilibrium at this point. The Q is, again, if we were to calculate Q, it would be equal to K again. What about for pressure changes? So generally the way we change the pressure of a gas without changing, you know, we could add more gas, but that, or take out some of the gaseous products or reactants, but that would be essentially doing what we just said, adding more reactants or removing reactants, or adding more products, removing products. But there is a way to affect the equilibrium in a gaseous reaction without changing what's in the container. What you do is you change the size of the container. So the best example of this that you're probably used to is an engine. So an engine has a piston, like the engine has several cylinders, right? The cylinders are firing, and there's a piston in your engine, and your engine, this one will go down, and this one will go up like that. And when the piston goes down, it's decreasing the volume and increasing the pressure inside of the container, and that the result of that in terms of your engine is that that causes it to have a very strong forward reaction, and then the gas blows up inside the piston and pushes it back out. But we can do that in reactions as well. We can change the size of the container, which will then change the pressure of the gases within that container. Just like if you squeeze on a balloon and decrease the volume, then the pressure of the gases inside will be increasing. So the way we determine what will happen in a reaction by changing the pressure is we have to figure out which direction will the reaction go that would correct that change in pressure. So if we increase the pressure, the reaction is going to go in such a way that it will reduce the pressure, which means that it will go in such a way where it goes from more moles of gases, which will have more pressure, to fewer moles of gases. Now, if we decrease the pressure, and that would be like the piston here going up and increasing the volume, so the pressure is decreasing, then the reaction will shift in, the equilibrium will shift in the direction that will produce more moles of gas and will thus increase the pressure. So here we have this example again with the Haber process. So we've got a mixture of N2, H2, and NH3, and it's at equilibrium, so Q is equal to K. But now we push the piston down, and that is increasing the pressure. So here we have increased the pressure because the volume has decreased. We pushed it down, and you know, if you would feel this, if you're pushing against the gas, if you have like hydraulic, what do you call it, shocks on your bike too, you know, you push down on it, and it's like pushing against you, right? The pressure is increasing. And so the reaction is going to shift in such a way that will decrease the pressure. So the way you figure out which direction that will be is you calculate how many moles of gas you have on each side. So on this side we have 1 moles of N2 plus 3 moles of H2. So on the left there's 4 moles of gases. Okay. Now on the right there's just 2 moles of gases. So the reaction is going to shift in the direction that's going to reduce the number of moles of gas if you increase the pressure. So we increase the pressure, so this reaction is going to shift to the right, because when this reaction goes forward, it goes from more moles of gas to less moles of gas. And you guys know PV equals nRT, right? PV equals nRT. And so basically here, if volume is the same, and so volume and temperature, these are unchanged, then a fewer moles of gas will mean a lower pressure. If the N goes down, then the pressure goes down. If the N goes up, the pressure goes up. So in this case, the N, the number of moles of gas, is going to decrease when the reaction goes forward. And so this reaction will go forward when the pressure increases. And then eventually it will get back to a new equilibrium. If the pressure were decreased, the reaction would go in the opposite direction. So there's a little bit more work to do when deciding what will happen to the equilibrium in the case of a pressure change. You've got to decide, which direction is going to result in more moles of gas or less moles of gas. If you increase the pressure, the reaction will go in the direction that will produce less moles of gas, thus decreasing the pressure. If you decrease the pressure, the reaction will shift in the direction that will produce more moles of gas, thus returning it to a larger pressure. And so again, we can do this same type of thing with Qs. Okay, so let's say we've got an equilibrium mixture here. It's 0.5 molar N2, 3 molar H2, 1.898 molar NH3. And we reduce the volume by a factor of 2. So if we reduce the volume by a factor of 2, what we're doing essentially is we're increasing the concentrations by a factor of 2. So we're going to be doubling each of the concentrations. So the new concentration for N2 is going to be now not 0.5, but it'll be 1.0 molar. The new concentration for H2, if we squeeze the volume in half, will be 6.00 molar. And the new concentration for the NH3 will be double this one. It will be 3.96 molar. And so we can plug that into Q now and calculate Q. So again, Q is the NH3 concentration squared, divide by the nitrogen, divide by the hydrogen concentration cubed. And so we'll put those in. So the new concentration here for NH3 is 3.96. We're going to square that. For the N2, it's now 1.00. We're gonna take that to the first power, and for the hydrogen, it's 6, and we're gonna cube that. And so now let's calculate this new Q here. So our Q is going to be 3.96 squared divide by 1 divide by 6.00. We don't really have to type the 0.00, but to the third power. And we get a Q that is 0.0726. Yeah, 0.0726. That is less than K. So Q is less than K. Q is less than K. That means that the reaction goes to the right, which is exactly what we predicted. So again, you know, if you have the numbers, you can always calculate Q and compare to K, and that will tell you which direction the reaction will go. But you don't have to do that to apply Le Chatelier's principle. We didn't have any numbers in the last example. We just knew that because the volume was decreased, that means the pressure of the gases inside were increased, and so the reaction had to shift in the direction that would reduce the moles of gas, which in the case of this reaction is to the right. Okay. Now finally, the effect of a temperature change on equilibrium. So when the equilibrium is disturbed by a change in temperature, Le Chatelier's principle predicts the following. It's going to depend on whether the reaction is exothermic or endothermic in the case of a temperature change. So the equilibrium constant for an exothermic reaction decreases as the temperature increases. So that's the effect of the temperature on the equilibrium constant, and I'll show you why. So that means the reaction is going to go more to the left here. If in an endothermic reaction, with a positive delta H, the K increases and temperature increases. So there's actually a very easier way of deciding what's going to happen here. What you do is you look. And for this reaction, for example, this is exothermic. So that means that this reaction is going to produce heat as a product. Okay. So once you've decided whether the reaction is exothermic and is going to produce heat as a product, or is endothermic and is going to have heat as a reactant, then you just think of temperature as adding or removing heat. So here, if we increase the temperature, that is going to be like adding more heat. We're going to put in more heat, which is a product in this reaction. So for this exothermic reaction, by increasing the temperature, that's going to add more heat, and now the reaction will want to go to the left to consume that added heat. Because when the reaction goes to the right, it produces heat. If it goes to the left, it will consume that heat. And so what you can see as a result here for the equilibrium constant is that as the temperature gets higher and higher, the equilibrium constant gets lower and lower. And this is a really important thing in a reaction like this. So you might have noticed that in the example we had before, the reaction was run in this temperature range. You may think, why not run the reaction down here then at 300 Kelvin, because that has an even bigger equilibrium constant, which means that at equilibrium there will be more product. And the answer is we don't run it at that low temperature because the reaction would go too slow at that temperature. Remember, reactions go more quickly at a higher temperature. And so there's often a balance in industrial chemistry of deciding, well, if we increase the temperature, that will increase the speed of the reaction, but it may decrease the equilibrium constant, which is something we don't want. So choosing the temperature at which you're going to run a reaction is very important, because a higher temperature will make the reaction run more quickly. However, if the reaction is exothermic, at a higher temperature, the equilibrium constant will be smaller. And so that means you will produce less products at equilibrium. Now, this is an example of an endothermic reaction here. And so this is that same reaction we talked about earlier of the that happens in the sky above LA, makes the smog, the NO2. So the NO2 is very brown color. This is an endothermic reaction. So delta H is greater than 0. And what that means is that heat is a reactant in this one. So that means if we increase the temperature on an endothermic reaction like this, if we increase the temperature, that's like adding more heat. And that's going to cause the reaction to shift to the right because this reaction is endothermic. It consumes heat to go forward, right? And so by increasing the temperature, it's like we're adding in heat. And so the reaction is going to shift forward to consume that additional heat. And you can see the result here. On the left, we have a ice water bath for this mixture of N2O4 and NO2. And on the right, we have a boiling water. And we can see at the hotter temperature, this looks more brown because at the hotter temperature, there's more of the NO2. But at the lower temperature, there's less of the NO2, so it's less brown. So for an endothermic reaction like this, increasing the temperature will actually cause it to shift to the right. And then one last thing about the effect of a catalyst. So we saw that we can affect the equilibrium by changing the concentrations of reactants or products, by changing the volume of the container, which in a gaseous reaction, which changes the pressure of the gases, and also by changing the temperature, which actually changes the equilibrium constant. What about a catalyst? So back in chapter 16, we talked about how adding a catalyst makes the reaction go faster. The important thing is that it makes it go faster in the forward and the reverse direction. And remember, equilibrium is when the forward direction is going the same speed as the reverse direction. So the result is that although adding a catalyst makes a reaction faster, it has no effect on the equilibrium. So the composition, adding a catalyst makes a reaction faster, but the composition of the equilibrium mixture is unchanged by the addition of a catalyst. Okay. Now there's one more section in this chapter about the actual mathematics behind the relationship of the equilibrium constant and the temperature. I generally skip that. I think that it's more important to practice the calculations of the equilibrium concentrations. So there's a short section on that in the textbook. I don't expect you to do the mathematical calculations there, but I do expect you to understand what we talked about here with the relationship between the temperature and what happens to the equilibrium constant in a qualitative way. Okay. And that's it for the lecture here on equilibrium. Remember, get a lot of practice in this week. This is going to be the foundation of a lot of the things we're going to be doing later in chapter 18, chapter 19. Understanding equilibrium is the center of this class. And so I encourage a lot of practice this week and coming to office hours or sending me emails, communicating with me when you get stuck, okay? And so, you know, have a good homework here. Good luck in your homework, and I'll see you in office hours. Have a good one. Bye.